Hello, I'm your chemistry teacher. Today we will study the Haber's process in detail. Basically, the Haber's process is used for the production of ammonia, and ammonia is manufactured using the Haber's process in the 5 stages. So there are basically 5 stages which involves production of ammonia, and let's discuss the stages in detail. You can see the over here in the diagram below. This is the first stage. In the first stage of the production of ammonia, you can see that nitrogen from the air, because air contains 78% of nitrogen, it is removed by the fractional distillation and it is then used for the Haber's process. So nitrogen from the air and hydrogen from the natural gas, the process which is called as steam reforming, we will use these two nitrogen and hydrogen gases, and they are pumped into the compressor, which is you can see over here in the stage number 2, we have got a compressor. So through these pipes, the nitrogen and hydrogen are compressed, are pumped into the compressor through these pipes, and these gases, after coming into the compressor, they are compressed to about the pressure which is 200 atm. So 200 atmospheric pressure is given to these gases and they are compressed over here in the compressor. Then what happens next is that in the stage 3, these pressurized gases are pumped into a tank which contains the layers of catalytic iron beds. And here, over here in this container, the temperature is maintained 450 degrees Celsius. So these are the reaction conditions for the production of ammonia, that the pressure is maintained 200 atm and the temperature is 450 degrees Celsius. So over here in the stage number 3, you can see that the pressurized gases are pumped into a tank containing the layers of the catalytic iron beds at a temperature of 450 degrees Celsius. Some of the hydrogen and nitrogen in this tank, they will react together to form ammonia, as you can see in this equation that I have written over here on the board. Nitrogen and hydrogen will react together to produce ammonia in this tank. But some of the nitrogen and hydrogen, they remain unreacted as well. So at the stage number 4, you can see in the stage number 4 over here, here we have got the nitrogen, hydrogen, and ammonia gases. In this tank number 4, at the stage 4 over here in this cooling tank, the unreacted hydrogen and nitrogen as well as ammonia, which is the product, it is passed into this cooling tank, which you can see in the stage number 4. So what happens in this tank? Ammonia is basically over here, it is liquefied and it is removed out to the pressurized storage vessels. We will get the ammonia. However, the unreacted gases, the nitrogen and hydrogen, they are recycled back from this is the stage 5. So you can see the nitrogen and hydrogen gases, they are recycled back into this system at the stage number 5. So these were the 5 stages for the production of ammonia. You can see that how basically ammonia is produced and the reaction conditions that are maintained over here in the Haber process. They are 200 atmospheric pressure, 450 degrees Celsius temperature, and you will use the iron catalyst in order to speed up the whole process, in order to speed up the rate of reaction for the production of ammonia. So now let's see the effect of change in temperature and pressure on ammonia synthesis, because you people know that this is a reversible reaction, and if a reversible reaction happens in a closed vessel, in a closed container, a dynamic equilibrium state will appear, and we will get the certain conditions. If we change the temperature and pressure conditions, they would affect the yield of ammonia production. So let's discuss the effect of changing temperature and pressure on ammonia synthesis. Look at this graph. This is the graph that is showing you the yield of ammonia produced while, like, at different intervals when we change the temperature and pressure conditions. So basically, the thing is that reaction conditions, just like temperature and pressure, they affect the rate of reaction. And if the reaction is reversible, then the position of equilibrium is also affected by changes in these conditions. And often we must consider a trade-off between the rate of reaction and the product yield. So you can see this graph is illustrating the effect of changing temperature and pressure on the yield of ammonia obtained. So you people can see that by following any curved lines on the graph, it can be seen that as the pressure increases, so too does the yield of ammonia as well at the given temperature. So with the increase of pressure, you can see an increase in the yield of production of ammonia. But like you can see by following the vertical lines upward from x-axis, the graph over here, it shows the decrease in temperature is favoring the increase in ammonia yield. You can see that whenever we are decreasing the temperature, you can see over here it is 550, the yield of ammonia production is roundabout, like it is between 20 to 25 percent. So you can see at 55 degrees Celsius, but where the temperature is very high, the yield of ammonia is like around about approximately between 20 to 25. But as we like lowers the temperature, we go up. We have low the temperature approximately to 350 degrees Celsius. You can see over here the ammonia production, it is maximum in here. It is around about between 60 to 65 percent. So over here we have got maximum production of ammonia at lower temperature. So low temperature is favoring more yield of ammonia. But you know that the actual conditions used must be chosen. It depends upon the number of economical, chemical, and practical considerations. So what are those conditions? How can we choose the reaction condition in order to obtain a maximum or optimum yield of ammonia? So for that purpose, there are like industries or the companies that manufacture and sell all the chemical goods. They do so to make the profit. And part of the industrial processes, it is an economic decision on how and where to design and implement a manufacturing site. So the availability and the cost of raw materials is a major consideration which must be studied well before taking any decision. So the availability and the cost of the raw material, it is like of prime importance. I can write it over here on the board: availability and cost of raw material. You must consider this because it is involved in the economic considerations while setting up the industry or the company that manufacture or sell the chemical goods to make profit. So, you know that in Haber's process, we have got the raw materials that are readily available and inexpensive to purify, because we have got the raw material in case of Haber process. We have got the raw materials which are nitrogen. Obviously, we will simply get the nitrogen from air by fractional distillation. it is cheap, it is inexpensive, as well as it is readily available to us. The other raw material which is used in the manufacturing of ammonia synthesis, that is hydrogen. You can see hydrogen is also obtained from steam reforming by natural gas. So it is also an inexpensive raw material. So the first process is that the availability and cost of raw material must be considered in order to maintain these conditions, in order to set up the uh, industry or the company. So you can see over here that if the cost of extraction of raw materials, for example, is too high or they are unavailable, then the process, that is no longer economically viable. And many industrial processes require a huge amount of heat and pressure, which are very expensive to maintain. So the production energy costs are also the factor to be considered carefully, and alongside the raw materials issue, you will consider those. The other reaction condition in the case of ammonia synthesis, the conditions that we have seen during these stages, they were the temperature and pressure conditions. So temperature was maintained. In case of the Haber process, it was 450 degrees Celsius. So it was 450 degrees Celsius, and the pressure was maintained. It was maintained 200 atm during the process for the production of ammonia. So why the industrialists have maintained these pressure conditions? This question must come in our mind. We can see that at a low pressure temperature, you can see over here, we can get maximum yield of ammonia. But the question should come in our mind that we can easily achieve this temperature without that much energy usage. So why aren't we stuck to at 450 degrees Celsius? You can see that a higher temperature would favor the reverse reaction, as it is, endothermic, so takes in heat. So higher temperature, a higher yield of reactants would be made in that case. But if a lower temperature is used, it favors the forward reaction, as in the case of exothermic that releases the heat. So that will yield a higher production of your products. So what happens in this case in the production of ammonia? You can see lower temperature is making a high heat, but uh, we aren't responding to the reaction conditions at 350. We have maintained it at 450 degrees Celsius. Why this is so? Because a lower temperature will decrease or slow down the rate of reaction. So 450 degrees Celsius temperature, which is the compromise temperature, it is made between having a lower yield of products but more quickly. We have made this compromise temperature 450 degrees Celsius. Why this is so? Because at this temperature, though we will get a lower yield, but the production of ammonia will be quicker in this case. The rate of reaction would be faster than that at like 350 degrees Celsius. We would have a very slow rate of reaction. That is why we have made a compromise temperature. We have established a compromise temperature of 450 degrees Celsius in order to produce ammonia. Similar is the case for pressure. You must remember that a low pressure would favor the reversible reaction, reverse into the reverse direction, as the system will try to increase the pressure, by creating more molecules. In this case, for the case of ammonia, you can see the equation over here on the board. So in this case, a low pressure will favor the reverse reaction, as the system will try to increase the pressure by creating more molecules, like 4 molecules of gaseous reactants are there, you can see. So a higher the yield of reactants will be made. So if we have got a higher pressure, what happens then? A higher pressure would favor this reaction in the forward direction, as it will try to decrease the pressure by creating fewer molecules, like 2 molecules of the gaseous product. So we will have a higher yield of products. In the case of the ammonia, production of ammonia, high pressures can be very dangerous and very expensive. Equipment would be required for to achieve the high pressure. Though high pressure is favoring the higher yield of ammonia, but in this case, they can like to achieve high pressure, that could be very dangerous, or very expensive equipment could be required for this. That is why a compromised pressure is maintained, which is 200 atm pressure. And to though at 200 atm pressure, we will have a lower yield of product, but being more safely and economically, we can make ammonia. That is why these compromised temperature and pressure conditions are maintained for the production of ammonia. Moreover, the other thing which is used for the production of ammonia is the catalyst. You can see in the stages we have used the iron bed. So iron is used as a catalyst over here, and obviously the presence of catalyst does not affect the position of equilibrium, but it does increase the rate at which equilibrium is reached. So this is because the catalyst increases the rate of both forward and backward reactions by the same amount, by providing an alternative path, where we can say by lowering the activation energy. So what happens as a result? The concentration of reactants or products is nevertheless the same at equilibrium as it would be without the catalyst. So a catalyst is used as it helps the reaction reach equilibrium in a quicker way. It basically allows for an acceptable yield to achieve a lower temperature by lowering the activation energy required, because without it, the process would have been carried out even at higher temperature, increasing the cost or decreasing the yield, as higher temperature decomposes more ammonia molecules. So this is the effect of a catalyst on the production of ammonia. You can see over here, this is a diagram just showing the effect of catalyst on the equilibrium position. It will increase the rate of forward and backward reaction. It will simply increase the rate of reaction of the production of ammonia. The other thing is that you must know that reaction conditions which are chosen for Haber process, though they are not ideal in terms of yield, but they do provide balance between the product yield, the rate of reaction, and the production cost. That is why these reaction conditions are made, these compromise conditions are made, because they are helpful in order to give a balance, in order to create a balance between, we can write it, they will create a balance between the production cost, or we can say the yield of ammonia production, and as well as the rate of reaction. That is why these compromise conditions are made. So this was all about the production of ammonia through Haber's process. Um, Hope you have understood it in a better way now. Let's see some of the questions related to the Haber's process for the production of ammonia. that. So look at the question. This question is about ammonia and fertilizers. Ammonia is produced from nitrogen and hydrogen. A catalyst is used to speed up the reaction. Word equation is given over here. You can see nitrogen plus hydrogen is making ammonia. So what does the symbol this shows about the reaction? Obviously, this symbol is telling that the reaction is reversible, because this is the symbol for the reversible reaction. Okay, so which catalyst is used when ammonia is produced from nitrogen and hydrogen? So obviously it is iron catalyst. Iron is a transition metal, and it is uh, used in the manufacturing of ammonia through the Haber's process. Okay, what's the other diagram? The diagram below shows the reaction profile for the production of ammonia, both with a catalyst and without a catalyst. Okay, this is the diagram, energy profile. You can see over here. Okay, this is the reactants. These are the products and the progress of reaction over here. Okay, what is represented by label X? We need to know what is this X, like this one, this, and this. What is this X? So let's see, this is obviously the activation energy with a catalyst. You can see with use of a catalyst, the activation energy is decreased because a catalyst always lowers the activation energy. So let's see, where's the option? Activation energy with the catalyst. Yes, obviously this is the first one. This is showing the activation energy with the catalyst, because at this point it is showing that this one of the activation energy, this curve for the activation energy is lowered. Initially it was this, but after the use of the catalyst it has been lowered over here. You can see, so the curve of the activation energy is lowered. So this is the activation energy with a catalyst. Okay, let's see the other one. This question is about the reversible reactions and equilibrium. Hydrogen is used to produce ammonia in the Haber process. The hydrogen is made in two stages. Stage one is given in the question. Stage one is the reaction of methane and steam to produce carbon monoxide and hydrogen, and we will use this hydrogen in the production of ammonia. We need to calculate the atom economy from the formation of hydrogen in this stage one. The relative atomic masses are given. So let's see, atom economy, obviously it is atom economy equals MR of desired products over MR of all the products. So, so I can write total MR of all the products. So let's see. My desired product is obviously hydrogen. So in this equation, you can see we have got 3 moles of hydrogen. So one time 3 twos are 6. It's 6. So 6, because hydrogen is my desired product, I will write 6 over here, divided by the MR of all the products, total MR of all the products, relative atomic masses. So you can see relative molecular masses. You can see over here we have got carbon monoxide. So for carbon it is 12, plus oxygen it is, the atomic mass for carbon is 12, for oxygen it is 16, and for 3 hydrogen molecules over here we have got 6. So we will add them up all. Okay, let me add it up. 12 plus 16 equals 28. This is 28. 28 plus 6, 34. So 28 plus 6 of this hydrogen, which is the desired product, it equals 34. So we will write it over here, 6 divided by 34 times by 100. Okay, let's calculate it. What will be our answer? Okay, it is 17.6%. So this is our atom economy for the this reaction. Okay, so it is 17.6%. Let's see the other question. It is that explain why a low pressure is used in stage 1. Give your answer in terms of equilibrium. Okay, so this is the thing that always whenever an equilibrium stage is established, in the case of the, obviously, you know, equilibrium established when there is a closed vessel and the reaction is reversible. So equilibrium is established. So this is also a reversible reaction. In this case, they are asking that why a low pressure is used in stage 1. For pressure condition according to Le Chatelier principle, we should know that how would pressure affect the position of equilibrium. Look at this table over here. Whenever you get an increase in pressure, you will increase in pressure of the reactant. What happens to the equilibrium? Equilibrium will shift in the direction that produces smaller number of molecules of gas in order to decrease the pressure again, because you have made a change to equilibrium position. What the system will do, the system will oppose that change. So the system will move to that direction in order which has smaller number of molecules in order to regain its position. So what happens if we will decrease the pressure? The equilibrium will shift in the direction that produces larger molecules of the gas to increase the pressure again. So in this reaction, you can see they have asked that why a low pressure is used, because when we are lowering the pressure, you can see that over here we have got on the right hand side, on the left hand side of the equation, you can see that we have got only two number of moles or two molecules, but on the right hand side we have got 1 mole for carbon monoxide, 3 moles for hydrogen. So on the right hand side, we have more molecules. So whenever more molecules of product. So whenever we will lower the pressure, lowering the pressure will shift the equilibrium. You can see will shift the equilibrium to that side, which will produce the large number of molecules. So it will shift the position to the right hand side and it will make more of our products. It will make more carbon monoxide and hydrogen gas. This is the answer for this, that explain why low pressure is used, because lowering the pressure favors more heat. Okay. So you would have a higher yield of hydrogen or carbon monoxide. So this was all about the production of ammonia. Hope so you have understood it now better. Okay, see you in the next class then. Take care. Allah Hafiz.